Okay, so today I want to show you guys something uh working on a little bit today. I didn't have time to finish it, so it'll be work in progress, but the bones are there. I've been thinking about how we could organize the code and architecture of the sidechain project. And after talking with Eduardo a bit about it, I realized blockchains are basically the same as web apps. So why not use the same standard um, web app architecture? Um, in my opinion, the how to architect a web app is kind of a solved problem. The Elm architecture seems really, really nice. So just you guys are probably familiar with it, but just in case you're not, the idea of the Elm architecture is that you have a single uh, global state, um, and you have views, which are pure functions from this global state to a DOM HTML, um, and then you have events that can be dispatched from these. Either like maybe a network request comes in or a user clicks a button. Um, and then you have a pure function from, you know, like the current state plus an event to the next state. Um, except like that, so that's the standard Redux model. In Elm, it adds another component. Instead of being the next state, it's a pair of the next state and the next action. Um, and then the Elm runtime executes that action. Um, so it's a lot like the IO monad. Like instead of doing the impure action, you construct your uh, your data structures that are interpreted to get the impure action. Um, and it makes it really easy to understand and test your state machine. Um, so I've partially implemented a very, very simple blockchain um, based on this Elm architecture, and that's what I'm gonna show you now. But first, I'm gonna double check that we are still recording. Yes, we good. Okay. Um, so if we look here, you can see that it's a React app. So it it's a React Redux app. So it uses the hooks interface provided by React Redux to provide the state to the app. You can see that here in View. Um, and I actually have it running right here. Um, so because it's a Redux app, it works with the Redux dev tools. So first we're going to connect to the peer-to-peer network that I'm using like a pure.js library to do this. And then you can see that it dispatches actions, which are like these pure JSON objects, and then they all get stored in this log here. And because this is all part of a standard uh, interface, we get all this amazing tooling for free. So like we can actually go back in time, and you can see like by clicking this back button, we're no longer connected to the network, or if we go forward, then we are. We can rearrange them, inject, go back, time travel, all of that stuff. Uh, and that's amazing for debugging. We can see diffs and stuff, traces. So yeah, we definitely need strong tooling like this. Maybe not the Redux tooling, although who knows? I mean, it'd be kind of neat to plug our stuff into the Redux dev tools. But yeah, we're connected to the network here. Now we're going to connect this one, and we're going to copy paste this ID. and connect to peer. That's all. That's as far as I've gotten, is finding and connecting to peers on the network, and they can send messages. But back to this. This is our view, and you can see we can dispatch actions. I'm going to make this bigger for you. So for any kind of feature that we want to add, it goes in one of 4 places. It goes in the view, like maybe it's an HTTP endpoint or something, or a query, or another user action. Or it's an action, which is like an event that happens, like receive something from the gossip network, or a CLI command. It's a side effect, which is some impure call to some API, but these side effects have to be stateless, kind of like REST endpoints, like the REST API says that like every endpoint has to be stateless. It can't depend on some kind of, you know, uh, state. Anyway, so what I mean by that, let me try that again. These effects can perform writes, but they can't perform reads. Like their only access to the state is via like their parameters. If that makes any sense. And then finally the reducers. And the reducers is where all the magic happens. Each one of these is a state machine. So let's look at the simple one, the peer-to-peer reducer. So this says, well, the signature of a reducer is always the current state and some action. And then it returns this command monad, which is a pair of the next state and some action, some action to perform. So when we see like the peer-to-peer initialization request, we return, loop is just like the, it's kind of like bind for the command monad. So we have, this is our next state. And then we run this thing. So this is our API. So this is saying, this is asking the command interpreter to call this function without any parameters. So, and then when you're done, this returns a promise. When the promise resolves, do this next thing. So this is a function from the result of this promise to an action. And so basically when the request is finished, a success action automatically gets dispatched. So when the success action gets dispatched, we hit this case, and then we actually do the state changes that this entails. So again, pure functions to construct impure sequences of actions. And the result is that this becomes much easier to test, because as opposed to something like thunks, everything is highly structured and organized. The trade-off is that there's a ton of boilerplate, but that's okay. That can be reduced with by extracting things into common functions or with macros or whatever. Um, it's a lot easy. Like the boilerplate is very, very easy to write, even if it's a little tedious. So yeah, this is all similar stuff. Something more interesting is the protocol reducer. So this is where we would implement the state machine of our protocol, and basically we're just implementing that flowchart that Eduardo made on Whimsical. So this is not easy to understand as I've implemented, and it's not finished yet. There's a lot of stuff I didn't get to, but even though it's not easy, it's not impossible to understand. And importantly, it's not impossible to formally verify, because like this is just a pure function. Like if you get this event, follow this. Like each one of these case statements is like an entry point into the flowchart. And then like receive block, you get this event, this is going right on the flowchart, and else is going left. So yeah, I mean, we could formally verify this thing, or we could, like Thomas was saying, we could construct this with a GADT that would verify a lot of properties. There's a lot we can do, and we could automatically, with macros, we could automatically generate flowcharts from this. But yeah, the point is, instead of doing the action itself, it schedules the action to be done. So there's often pairs of actions. You can see first we make a request, and then we get the success event for it. So another component of this is that is very, very modular. The protocol reducer knows nothing about the peer-to-peer layer, and they're coordinated through another pure function, so called top level reducer. I'm not set on this pattern, but this is the best I could come up with on a Saturday morning. Basically, top level reducer knows the entire state of the node. And what it does is like it routes actions to their different sub reducers. So if there's a peer-to-peer action, then it routes this to the peer-to-peer reducer. And then it optionally adds on follow-up actions. So for example, in my simple blockchain, every peer is considered to be a validator. So you can see after we run the peer-to-peer reducer, then we also say if the action was a successful connection to a peer, then map that action to a add validator action. And then that will, so that's how the peer-to-peer, like this top level thing is how the peer-to-peer layer interacts with the protocol layer through kind of like a inversion of control type thing. I mean, this top level reducer would get messy quickly. But we can have like this fractal structure where there's like reducers inside reducers inside reducers, and each one is relatively simple to understand. And again, like this could map to a flowchart. So now you have flowcharts within flowcharts, and understanding any one flowchart probably wouldn't be too difficult. And it wouldn't be too difficult to verify. So the great thing is that I think, oh, like this can handle parallelism easily because you just have like you have a request to the other thread, and then eventually that thread puts a success or a failure back onto the main thread. I mean, this can handle pretty much any consensus mechanism, I think. Uh, and it can handle any smart contract language because the smart contract language is just a like a sub reducer. Um, and the great thing about this is there's very, very little question as to where to put code or how to get started on any particular feature. Because if you're implementing a flowchart, then it's a reducer. If there's any side effect, then it goes in the effects, and you can copy these, and you know that it has to be a stateless effect. Like, it can do an impure thing, but only based on the parameters that it's given on its inputs. Or if you're creating an event, it goes in actions, and events are just pure data. So they would be like variants in OCaml. So yeah, it's been my experience that when like the teams that I've worked on have switched over to this architecture, it's been much easier to uh, communicate like what you want done or get started or test a feature. So yeah, I'm just putting it out there for y'all's consideration. Thanks for watching.